Well, it's time. It's time to. Thank you for watching.
Okay, good morning, everybody. Welcome back. It's my pleasure to announce the third part of the stochastic analysis course by Paulo Rufino. So,
Right.
stage is yours.
Thank you very much, Tom. And good morning, everybody. Here we are again for the third lecture, or rather talk. Before we start, we have a nice property. There is a red car just parked opposite here, which is where the lights are on. Is anybody car? Right. Okay. So before we start, this is a simple exercise, and we are going to use this. Is very well known that if M is a martingale, continuous continuity here is important, and if X is a bounded variation process, for example, we have seen that quadratic variation of martingales, they are all of finite variation. Then the crossed variation between M and X is always 0. It vanishes. It's well known for maybe most of you. Maybe not. Well, it's just, in fact, it's just 2 lines. So in fact, so what we have to calculate is the limit in probability of the sum MTI plus 1 minus MTI x TI plus 1 minus XTI. This is precisely the definition when the mesh of the partition goes to 0. And we get this result easily when we write that this is smaller than or equal limit in probability when the mesh goes to 0. We can take the sup MTI plus 1 minus MTI sup into I, and the summation over XTI plus 1 minus XTI. And this goes to 0. So this is finite variation, is bounded, and this goes to 0 by continuity. It's an argument we have used before, simple argument, and without any integration, it's just simple and quite useful. We are going to use this many times, and we finished last lecture yesterday with the following theorem, or the formula, that the quadratic variation of stochastic integration can be easily calculated. Integration from 0 to t of x dm, integration from 0 to t y dm can be a different martingale as well. You will realize easily that this is the finite variation process given by xt x, x, y, integrated with respect to the quadratic variation of m. As simple as that, and this is again, as expected, of bounded variation. This is a simple integral, Riemann-Stieltjes integral, our well-known. So as I said before, I give an idea of the proof for elementary processes. So proof, rather an idea of what is going on. We take elementary processes. So as we have used it yesterday, this is x0, which is f naught measurable, 1, 0, t1, etc. I1 up to k or infinity, doesn't matter. 1 t I plus 1 t, sorry, t and random variable x. And yesterday we found it more convenient to use the upper index, where xi is f ti measurable for all I 0, 1, etc. Then by definition, the quadratic variation we are looking for is a straightforward calculation. And we are calculating the quadratic variation of xi, mti plus 1 minus mti against, in the sense of against in the sense of this inner product of martingales, y I summation of mti plus 1 minus mti. And this is by definition, precisely the summation of x, I, y, t, similar. This is, by definition, x, I, y, I, mti plus 1 minus mti square. And when we make the mesh going to 0, it converges in probability to exactly what we want, which is a summation xi, yi, quadratic variation of m at ti plus 1 minus quadratic variation of m at ti. So what the mesh going to 0 affects is this bit. This bit is fixed. They are constant in the interval, so it doesn't matter what happens with the mesh of the partition. Okay? This is precisely the integration of xs, ys, dm, s, as it is in the statement. It is a, well, two-line proof for elementary process, and then you just take the limit, and as I said, it's Right, it gives an idea of what is going on. So it is partially the idea of what is happening here. Okay. Examples. So quite simple. So say one wishes to calculate quadratic variation between integration of Brownian motion with respect to itself against integration of whatever, say h, a process or a function or adapted process with respect to bs. This is easily 0t hs, whatever it is, integrable, of course, gs, which is the quadratic variation of the Brownian motion. Simple like that. Bounded variation on the right-hand side. Right? Increasing and adapted and all nice properties. Continuous. Finally, before we start Ito formula, another simple property is the associativeness. In the following sense, if we have a process, say a martingale with h, gm, whatever is h, a adapted process continues without the good properties, but whatever it is, we write this in the infinitesimal form that dx equals h dm. This is a martingale if m is a martingale, as I said before, as we proved yesterday. So it means in the sense that if we are going to integrate g with respect to x, this is simply an associate g h gm. This is a property which deserves a proof in the sense that, well, it's a good exercise and can be easily understandable through elementary processes. So I leave it as an exercise. Again, for elementary processes. Starting with that. Finally, I haven't mentioned that stochastic Ito integration extends to semi-martingales, which is what I'm going to define, and then we go to Ito's formula, which says say x is just an extension, is a semi-martingale if x can be written as a martingale part plus a process of bounded derivative. In fact, can be a little bit more than that. This is bounded variation. Not necessarily continuous, but CAD-lag is good enough. M, a martingale, or rather a concept which I didn't introduce here in this course, which is local martingale. I mean, can be extended. I'm not entering into this realm. Local martingale Local martingale is an extension of the definition of martingale, which says that a process M is a local martingale if there exists a sequence of stopping time such that each M stopped at t or tall n, or if you prefer, t and tall n. For each n, tall n is increasing to infinite, and they are all martingales for all n. This is the concept of local martingale. I'm not going to explore this. Just keep the idea that semi-martingale is something, for this mini course, is something which is a martingale plus something of bounded variation, right? Most of time here for us in this course, n is going to be continuous. A not necessarily just bounded variation and can be Cadillac. Maybe even continuous is not. It depends the application you are going to do after this mini course, right? Right. And so stochastic integration, now Ito integration extends easily. So to y dx with all the conditions we stated yesterday on adaptedness of y, on integrability of y with respect to the quadratic variation of x, but essentially y belongs to L2 of p cross dx. So if y, the hypothesis to carry on the integration is this, which in fact is where I proved the Ito isometry. Is an isometry in this space into the space L2 of P, right? If you remember, and you do, yesterday lecture. So it extends easily by linearity. This is y. When x is written as a martingale plus bounded variation, this is simply y dm plus integration of y dA. This is a fantastic decomposition which says that we isolated the martingale part of the process and the bounded variation part of the process. Okay, so this is simply the Riemann-Stieltjes integration, simple like that. So Ito plays a role only here. Okay. Well, let's do the Ito formula now for semi-martingales. So Ito doubling. So this is more recently in the last few decades, especially Europeans like to be fair with this mathematician who died in the Second World War. You certainly know this the history. So it's just that it's not exclusively of Ito, but it's paying respect to him as well. So this is a Ito or doubling formula. Right. So it says the following. So let's take xt a semi-martingale in Rn. Rn a semi-martingale continuous. And f a function from Rn to R, which is of class C2, at least. Then here comes the formula, which says how we can compose differentiable function with semi-martingales. And the formula says that semi-martingales, the class of semi-martingales are invariant by composition with C2 functions. As I said before, everything I'm presenting in this course are classical results, and many of these results, well, any topic I have mentioned has extensions, has new extensions, new weakened hypotheses, and interesting things has been done. Many people have results taken differentiability less than 2, much less than 2, surprisingly less than 2. But it's not the case for classical course for showing the classical results. Okay, so let's assume C2, then the proof goes in 2 lines. Then the composition of f with x of t equals. It is in fact a Taylor formula somehow, plus the integration from 0 to t of derivative of f with respect to each coordinate is a sum. A sum in I up to n, derivative of f with respect to each coordinate, integrated with respect to this coordinate. The derivative is calculated at xs. I am omitting here for sake of notation. Plus the second order term, which is a summation on ij from 1 to n, integration from 0 to t, second derivative of f, dx I dx j, integrated with respect to the crossed variation between I and j. Again, here there is an xs, which I'd rather omit for sake of clearness. So it says that differently from ordinary calculus, instead of a first order, we have a second order calculus. We need an extra term which involves the second derivative of f. Mind that if x has bounded variation, is a process of bounded variation, all the second term here, the second order term vanishes, right? So, and we are back in the classical calculus. Right. What else? If x is a martingale, we have explicitly isolated the martingale part and bounded variation part, right? So before I prove, or rather I give an idea how to prove for n equals 1, and then you understand easily what is in there. But a simple example, if f of x, this is a simple exercise which I left yesterday or the day before yesterday. If f of x equals x squared, then we have that we compose F with the Brownian motion. And what we get is that the square of Brownian motion equals 2 times 0 plus 2 times BS GBS from 0 to t plus half. Second derivative equals 2. Second derivative of 1 integrated with respect to quadratic variation. Simple like that. And we conclude that that BT square equals a martingale plus T. You should remember that I said before there was an exercise to prove that BT square, is it right? 2 twice, sorry? Yeah. It's done, right. Yeah, that was the exercise which could be done on those days, in those ideas, with just the definition of martingale is still possible to carry on by hand without using Ito formula. And I mentioned you that Ito formula is a source, is a natural source of martingales. So we can go much further on this. And in fact, if I have here further examples as exercise. If I did not mix up the powers, I hope not. Please check. One, that BT to the power n minus n minus 1 over 2, integration from 0 to t, bs n minus 2, ds are martingales for all n greater than or equal to. Right. Well, let's come back to the proof, and then we carry on with more. Except this, well, the rest of stochastic calculus is applications of this formula for forever. So a proof, or as usual, the idea of the proof. Take n equals to 1 just to fix the ideas. And we are going to write the following way, that f of xt, we are going to make an application of a Taylor formula. This looks as a Taylor formula, so it's not a new idea. Minus f of x0. The new idea was Ito's idea to take limit and probability. This is really revolutionary in stochastic calculus, but not the Taylor expansion. So this equals, I make a telescopic cancellation, and I rather take care of the index here. We had an experience with subindex yesterday, which is I'm not good at this. So f of x ti plus 1 minus f of x ti for a certain partition, 0, Tn. Is it okay? The indexes, am I starting at the right place? I equals 1? No. We have to start at 0, right? Please help me. Yeah, thank you. Right, this is a telescopic cancellation, and we calculate each of this. We calculate each of this, I mean omega y's, path by path. X ti plus 1 minus f x ti. This can be written, if you have chalk, so this can be written as the first derivative, sorry, of x at x ti plus 1 times x ti plus 1 minus x ti. So this is the first order of the Taylor series plus the second order of Taylor series with Lagrange remainder for some psi between xti and xti plus 1. So, and this is a second order, ti plus 1 minus xti to the power 2. Okay? So this psi, for the moment, is a random variable, but it doesn't play a role at all. Why not? When we plug this up there and take the limit in probability, this doesn't play a role at all. This converges. This converges when the mesh of the partition goes to 0. Not only on probability, but it converts pathwise to half integration of the second derivative of xs integrated with respect to the quadratic variation of x. Simple like that. So what we are doing is that we are taking summation here, summation there, take p limit and p limit. Is it clear? So what is happening here? What? This is the definition of the Ito integral. No. No. This is on the left-hand side of the interval. Right? Taylor's formula is. I am interested in this with respect to that. And this converts in probability, and the mesh goes to 0. This is the Ito integration f prime x s gxs. Okay? So it is it gives an idea of what is happening there. It is Taylor formula with a limit in probability. Simple like that. Well, nowadays it's simple like that. But 17 years ago, it wasn't so clear. Yes, please. A question. I'm sorry? Right. This is a Taylor expansion with Lagrange remainder. No, just rely on normal analysis. So we don't need to prove it separately. It works path by path. Right. Okay. This is a Taylor formula with Lagrange remainder. And what's happening more precisely is that psi is between x ti plus 1 x ti, or in the other way around, depending which one is biggest, or the other way around. Okay, it's classical Lagrange remainder. Yes, and NG. Well, I am it's a semi-martingale to I am using it to get the Ito integral well defined. Otherwise it's absolutely unknown. So otherwise it will be absolutely unknown if it's not a semi-martingale. So we have constructed a theory of integration sitting on martingales and semi-martingales. So, okay. So this is Ito integration. Okay. So this is philosophically speaking, if we have a theory of third order, if we have a quartic variation or p variation, then your theory you have to go further up to order p, just to satisfy and define all sorts of integration. This is a naive and philosophical idea. What is happening here is a theory of p equals 2 variation. So this is good enough to stop at 2. There is no theory for a higher. Yes, it's a Roth-Path theory. Yeah. So that's the continuation of the classical stochastic calculus. Stochastic second order calculus is to higher p variation or lower alpha Holder continuous with the alpha small. Okay. Right. One more example, which is related to stochastic equation. Oh yeah, sure. Thank you. Switch it on.
Hello?
Yes.
The Xi random variable, it is not FTI measurable. Doesn't it need to be?
Say again.
The Xi random variable in the Taylor expansion.
The psi.
Yes.
Right.
It is not FTI measurable. Doesn't it need to be?
No, it doesn't. No, we are not taking stochastic integration. This is usual integration.
Oh, okay.
It's not even relevant if it is measurable or not, if it's a random variable or not. Right? Classical Riemann-Stieltjes theory is good enough. It's a good point. Thank you. Well, with higher dimension, it's just higher dimension is just longer calculations, but it's the same idea. Right. Another example we have done before. Also possible to calculate by hand the conditional expectation that is a martingale, and now we can easily show that it's a martingale is the exponential, which is one step in the direction of stochastic differential equation. So if we have exponential of alpha x minus alpha square y over 2, and we calculate ft, bt, and t. Is t a semi-martingale? Of course. Yeah. So with the martingale part equals 0. So so we have that exponential of alpha bt minus alpha square t over 2. So you did the calculation explicitly. It's 2 or 3 lines of calculation to show that the conditional expectation of this equals the same function at s. And now we have a trivial way to show that it's a martingale. This corresponds to 1 at 0 when bt and t equals 0, plus the derivative with respect to bt from 0 to t. This is alpha exponential alpha bt minus alpha 2 t s g bs plus derivative with respect to t, which is minus alpha square over 2 exponential alpha bt minus alpha square t over 2 ds from 0 to t plus second order derivatives plus half second order derivatives. The derivative with respect to b is alpha square exponential of alpha bs minus alpha square s over 2 gs, which is the quadratic variation of the Brownian motion, plus the derivative with respect to b, the derivative with respect to x and y, which is a component here, integrated with respect to Brownian motion and t, plus something which the derivative with respect to x and y, then y and x, so this is twice, it appears twice, plus something which is the second derivative with respect to t. And we don't care about all of this because they are all 0. They vanish since t has bounded variation. This is the first exercise I have done. So essentially, we end up with this expression, and this is the opposite of that one. So we cancel out this and that, and we end up that what we were, the expression we have, this exponential, this stochastic exponential of Brownian motion is a martingale. All the bounded variation components vanishes. There is, thank you. 0 t, and half applied to all of this. Okay, so essentially we have this expression which solves the following equation. dxt equals xt dbt. This is a linear equation, one step, linear stochastic differential equation, ITO, in the ITO sense. And xt here, xt is the stochastic exponential. Some people call it the geometric Brownian motion. In mind that if for all martingale, if MT is a martingale, the same formula holds with quadratic variation of m in the place of t. So exponential of alpha mt minus alpha square quadratic variation of mt over 2 is the stochastic exponential of this martingale, or the solution of a linear equation taken in the sense of Ito. Okay. Further applications. Again, a simple formula to be proved is the integration by parts. Simple and useful. Integration by parts formula. Which says that if mn are continuous martingales, then we can easily calculate, or somehow easily calculate, the integration of one with respect to the other using that mt times nt equals m0 n0 plus integration of m gn plus integration of n gm plus the quadratic variation. Well, there are many examples and many applications, exercise, etc. I think it's time to introduce the Stratanovic integral, and we accelerate a little bit, if it is okay. I think it's most of this is well known for many of you, right? So the Stratanovic integration has been mentioned yesterday by Sebastian in the RALSPAS course. And here comes the definition. Stratanovic integration. So x, the integrand with the integrability condition as before, M a semi-martingale, continuous semi-martingale, then the integration of x with respect to M, and to distinguish to Ito integration, most people in literature just put a circle, a little circle in front of G. There are many alternatives, but this is the most common. And this is exactly the limit, the same P limit when the mesh goes to 0, the mesh of the partition goes to 0. Instead of taking I, well, I'm taking the summation on I, so well, this, for any partition, this is x ti plus 1. So no longer the left-hand side of the left-hand side of the interval of the partition, but an average of this 2 mti plus 1 minus mti. So it's pretty much interesting. The Ito formula for integration like that turns out to be much simpler than Ito formula. We are back in first order calculus. But before that, let's just compare Stratanovic with Ito integration. It's just a correction term. Ito Stratanovic, in the sense that the Ito integration equals Stratanovic integration plus P limit in probability of x ti plus 1. We subtract that term. Oops, no, we subtract this term, right? Minus x ti ti, we subtract this term, ti times m ti plus 1 minus m ti. This is divided by 2. So essentially, the difference to Ito is that we introduce an element which is anticipative with respect to the sigma algebra T1 at Ti. This is anticipative with respect to sigma algebra, and Ito doesn't do, so we subtract this, half of this. This should be, we have to add an extra term xci over 2, and then multiply by m. And this is, but this is precisely half of the quadratic variation between x and m. And this equals half of the quadratic variation between x and m. The sign Minus, well, it's minus, right? Ti. Yeah, it's minus. It's minus. Okay, let's see examples. So they are pretty much correlated to each other. So somehow, if you make a model, if you have a problem, make a model in terms of Stratanovic equation or in terms of Ito equation, you can easily change one from one to the other, just adding or subtracting quadratic variation. Okay. Right. Some initially simple examples, and then how it works in terms of the Ito formula for Stratanovic integration. So if so, what's the difference if we want to integrate our favorite process BS with respect to BS? This is a martingale. BS Ito, hence martingale part, minus T over 2 plus, sorry, I'm mixing, this is minus, right? This plus T over 2, which we know is BT squared over 2, which we have just calculated in the previous example, right? So nothing new in this, and mind that we the most important part, as I have already mentioned, and I repeat, I emphasize that Stratanovic is no longer a martingale, and this simple example shows explicitly that. So we have a integration with respect to Brownian motion, and we have a martingale and a bounded variation component. This is BT square, which is far from being a martingale, right? So just some a simple remark, which is somehow trivial, that the two integration coincides if the quadratic variation equals 0. So if we integrate independent Brownian motions, B1 integrated with respect to B2, and they are independent, then it doesn't matter if it is Stratanovic or Ito. And the remark is that for X, this is a martingale if M is a martingale. So if the semi-martingale M is a martingale and quadratic variation equals 0. For example, in Wiener integration, is you just integrate a function is a function in normally in F2, so we integrate this. So it doesn't matter if it is Stratanovic or Ito, since the quadratic variation vanishes. Okay, Ito formula for Stratanovic integration, which is quite useful, especially when we are observing geometric aspects.
Sorry,
Yes.
I don't really get the difference between Stratanovic and Ito's integration, because you said the Stratanovic integral could be work with a semi-martingale, but you already show us that if M is a semi-martingale, you can separate it, the Ito integral into a local martingale and bounded variation.
Right.
So, what do we really gain in this new kind of integral?
I'm sorry, I think nobody minds. Can I take out the mask? Thank you for. The integrator, which is M, the integrand and the integrator is again a semi-martingale. Can you say again what's? Oh, right. Yeah. Yeah. Well, we can do exactly the same, but it doesn't play any rule, because integration with respect to martingale doesn't play any rule, because it's going to give us something which is not necessarily a martingale. So up to now, there's no difference on separating it or not. Okay. Good. So Ito formula for Stratanovic integration. Ito or Dublin. Ito formula for Stratanovic integration. And we are back, as I said, in a first order calculus, which helps a lot on doing geometrical calculations, changing coordinates, pushing stochastic differential equations from one state space to another state space via differentiable maps. So this is essentially without depending on the second derivative. That's what I mean. So here comes the formula. So if f is from Rn to R with an extra degree of differentiability, which is again questionable, and we can reduce some people, but classically is C3, and what we are assuming. So x again, x1, xn, a semi-martingale, a continuous semi-martingale in Rn, then the formula is as simple as that f of xt is a process given by f at the initial condition plus summation on I equals 1 up to n, integration from 0 to t, derivative of f with respect to xi at point xs, integrated with respect to Stratanovic gs, and that's it. And we simple like that. Man. This is also in the Ito case. I didn't mention this is many times substituted by the derivative or Jacobian of f integrated with x. So it's a notation that you are doing coordinate wise. So the summation is inside here, or this is the covariant derivative and gx. So there are many alternatives here. As in the previous Ito formula, which is no longer there, then the second order term can be easily written as a Hessian of f, but it's just a short way to describe all these equations. But let's fix on this rather simpler and fruitful way to deal with stochastic calculus, which are Stratanovic equations. We had a short discussion here. So which one is the right one? So this is pointless. There is no right one. It depends on what you are modeling. So is your model a Martingale? Then no doubt it's a Ito equation. You are modeling something which is geometric. It will be easier to manipulate to make the calculations Stratanovic, but it all depends on what you want. They lead to different kind of processes with correction formula. So it's not too bad. Right. So let's prove this formula. So essentially what I am doing is another easy exercise. I'm just going to expand.
Sorry.
Yeah. Right.
Going back to this point about different applications having different integrals being useful, do people also investigate other quadrature formulas for the xt? For instance, this is like the trapezoidal rule, no?
Other
so
sort of integrations.
You say xti plus 1 plus xti divided by 2. So you kind of like take what's at the midpoint of the interval.
Right.
Right. Do people use, I don't know, other quadrature formulas if they want to get certain?
That's right. You can adapt here. You can take it an alpha multiplying here and then 1 minus alpha multiplying here and make all sorts of alpha Stratanovic sort of integration and find a different correction term, and you can develop all of this and many others. In the book by Reviews in Your, which I mentioned yesterday, which is a comprehensive book, there is some exercise there with some variation on the points where you are integrating. The left-hand side is the classical. I mean this one is the Ito and the canonical. And then we play around, and people do that, and it's really interesting, and it opens in many interesting areas of research.
Okay, just one.
Papers.
Is Stratanovic the only one which gives you a first-order calculus, or are there other rules which also give you first-order calculus?
Well, as far as I know, this is the only one which fits well with geometry, which is first order.
Okay.
But we can see easily for any alpha, as in the exercise in the reviews in your, with any other alpha, with the correction term would be different from 0.
No, I think my question was, so say you included not just the endpoints, but... No, sorry. Okay, no, that does make sense.
Right, okay, thank you. Yeah, Angie?
More general integrators, I guess. Is that the point of these modifications?
Oh yes, it's the point is to enlarge the class of integrants. Yeah, definitely. Yeah, it's
But
another point.
in that case, the integrand, it has the same conditions. So the integrator is what we generalize.
Right. Yeah. So no. Well, we are not. I'm assuming the same adaptedness and integrability condition which we assume to Ito formula, to Ito integration. Just to make it comparable. Right.
So basically, in Stratanovic integral, we can take less condition for x,
Less restriction.
more restricted x, or not. We have to take the integral conditions
More restricted to S.
x.
To X. No, no. It's the same condition of Ito integrability and Stratanovic integrability. So if it is Ito integrable, it is Stratanovic integrable. I don't know the answer of your question. If we can enlarge or not the class of integrands in the Stratanovic. The class of integrators of M. I don't know. Probably, yeah. Well, I'd rather ask somebody who do some research. Does anybody knows the answer for this question? But it's well, nowadays, as I said yesterday, and I repeat, each point I'm presenting here opens to large areas of research to increase in tens or hundreds of new papers with getting out of this classical approach, and including anticipative calculus, things, objects which are not adapted, and the meaning of that is well, it's all interesting. It's a fantastic realm, but huge. Each of them, right?
Right, thank you. I wanted to ask about this alpha here. If alpha is not equal to 1 or a half, so not Stratanovic or Ito, what would be the application for that?
I don't know, but it's you might want a model which is a little bit anticipating, but not too much, and then that's I don't know.
Okay, thanks.
Okay. Of this is alpha, right? So you might want a little bit, but not too much, or you can make all sorts of variation in your model.
I don't know
Yes,
if I
please.
missed it, but what's the reason for this C3 assumption in it?
It will appear in the proof, right? I'm going to take the third derivative.
But you don't need it for Ito.
No, we don't need it for Ito. So probably we can get rid of that with alternative proof, but I'm going to show you one proof, which is two-line proof. That's the point. And for this simple proof, it's a C3. And then we can investigate the weakening this hypothesis.
So,
Good question.
But for the proof you're going to show us, you need it.
That's right. Yeah.
Okay, but you don't need it in general.
We don't need it in general.
Okay.
Yeah, we don't need it in general.
Okay.
Uh,
That df dx you wrote there, so I'm not too sure what you meant because it's a bit sort of dangling in the. So what do you mean by df dx?
df dx. I mean the Jacobian of f. So you can see it as a matrix of derivative, and this is dx1, dxn, and the Jacobian of f. So this is precisely what is written here. It's just a nested notation.
So it's the Jacobian evaluated. So you can express that using the Jacobian, you're saying.
That's right.
Okay.
Yeah, that's right. So this is, you can see this as a map from Rn to linear from Rn to Rn. This is precisely what I mean. And dx is acting here, right? And this is also helpful in the geometrical context, because this is again a linear map from tangent space to tangent space, and so it's just a alternative notation. But this is what I'm going to prove. It's the classical view, but it's right. So it is. You mean the gradient? You mean sorry? I'm sorry. I'm sorry. Yeah. This derivative is not. This derivative is not. Sorry. I'm sorry. You're right. This is the gradient. This is the gradient of f. Or if you have an inner product, and we do in Rn, then this is the gradient of f. Gradient of f dx. Right. Thank you. Circle. Yep. Something like that. Yep. Yeah. So shorter notation is quite useful. So keep what I intend to write here. So this is still the derivative of f. So it's just the gradient, not Jacobian. So you're right. It would be if we are in higher dimension. That's right. Yeah, it's a sequence of gradients. Yeah, that's right. Yeah. So keep your eyes open to more nested way to write all these equations, and then we can include many. We can include, and this is I missing here as well, right? Yes, we are taking the derivative in the ith coordinate and integrating with the ith, with respect to the ith component of the semi-martingale. I'm sorry for that. It's just that the chalk, it doesn't work very well. So the I was there, but the chalk didn't fix it. Right. Thank you for that. Right. So we already believe that if this is Ito integration, we will need a second order and a second order terms summation on the Hessian and blah blah blah, or whatever. If you don't like Hessian, it's just a second order derivative, which is not relevant now. But if once Ito formula is given, so what I'm going to do is to prove that this integration with respect to Stratanovic, when we transform via correction term, we are back to the Ito formula, to the classical Ito formula. That's all we have to do. Do you understand what I mean? So the proof is that the integration of f with respect to xi dxi, I'm going to prove that this is precisely what we had before. Xi Ito. Well, let's state that f goes from R to R, so n equals 1 again. So there is no I here. plus plus half of the second derivative of f dx dx. Zero t. So this is what we have to prove, right? So if we have it proven, we get this Ito formula for Stratanovic, and this is. But we know that there is a correction term from Stratanovic to Ito integration, and what we have to do is to add half of the quadratic variation. So this is a claim, and this is a claim, and this is part of the proof, plus half of derivative of f dx at xs or xt xt. This is part of the proof. So what we have to do is to calculate this, star. And it's not difficult. It's not difficult, since we can write this, we can apply Ito formula on this function, right? We apply Ito formula on this function. We distinguish what is Ito integral or not. Then we can calculate the bracket of an Ito integral with respect to x of t. And then the quadratic variation of x will show up. Simple like that. So, so we have to apply Ito formula here. Ito formula says that this equals x0 plus integration from 0 to t, second derivative xs gxs plus half integration from 0 to t, the third derivative of x at xs xs. Is it? So if there is any martingale or there is any relevant component in terms of quadratic variation, it will be here. So any martingale component will be here. So it depends on x, right? Because this is of bounded variation. So when we make the crossed variation of xt with the bounded variation, so this component is not relevant in terms of this quadratic variation, right? Then we end up with concluding that the quadratic variation is exactly the first formula I proved today, which is the integration of the product f dx dxs. And we are done. We are back in the Ito formula for Ito integration. Is it clear? Right. So I didn't. This is the third derivative, which I didn't want to get any problem with that. Right. So example of what happens with the same linear equation we had before. Much easier now. But much less property, but much less probabilistic properties. I mean, Martingale is the key point, depending on your model, depending on what you are interested. So an example, if we consider, again, the same linear equation integrated with respect to the Brownian motion with some initial condition, x0 equals 1, then the solution is simply xt equals exponential of bt. Simple like that. Instead of correction term as we have in the Ito case. And all the calculation, all the integration just follows the same rule. So whatever integration you take from classical calculus, classical analysis, and this is Stratanovic, then this is going to be arctangent of BT. This is just etc. I mean, any integration which you are going to perform with respect to the same Martingale, you just apply immediately formulas, well-known formulas from elementary course on calculus. How are we doing with the time? I am going to introduce, 10:30. I think. Well, I'm just about to introduce stochastic differential equation, and I restart tomorrow. But basically, are expressions like that with Ito or Stratanovic, and we are looking. Can be more elements here with independent Brownian motion or independent Martingales, and with as many semi-martingales as we wish, and we carry on with that. The definition of a solution of that. But you already have a glance what is happening. So we carry on tomorrow. Thank you very much.
Do we have any questions? Seems not to be the case.
Okay. Well, no formalities, just. Sorry?
Posso te perguntar direito? Se você quiser calcular uma integral de Ito, é mais fácil calcular entre a integral de Stratanovic e depois calcular o término de correção?
Ah, sim. A maioria das vezes, sim. Isso. Opa.
Mas eu não conheço as regras para... Porque com a integral de Ito tem algumas técnicas.
how it's work.
You can find these results, but the answer, based on the fact that modulus continuity but it's harder finding this F variation. Where F is like x squared log function. Kentucky and I'm not sure if my wife wants to. In other countries, I try to have that. I'm a postdoc at the University
Okay, I think we can start with the next talk. So next up is Mazia from Fernuni Hagen, and he will lead the exercise class on rough paths.
Thank you very much for your introduction. I also want to say thanks to the organizer for their hospitality. Okay, today I want to hold the SPSAS sheet for our course, which we learned in last two sessions. In this course, I mainly focus on the more regular case, on the Young sense, but in the second exercise session, I try to focus on the more singular cases. So before going ahead, I just want to just give you a summary about our notation and what so far we learned. Okay, remember, okay, we always say C is, we use this notation. When X actually has the component such that this guy is finite. And we say ST T minus S is infinity. Okay, this was the notation, and definitely what by this notation, I mean the difference of the increment. And also we just learned if we take a C alpha function and assume X be C beta such that alpha plus beta is strictly larger than 1, then in the Young sense, we always can make sense of this integral. Or maybe use it in this way. U dxu, and we have this inequality. ST alpha ta t minus s alpha plus beta. Okay, this is just a quick summary. Okay, the first exercise is quite easy and elementary, but because of the importance I just stated here, assume this is actually a lemma which we use it many times, but again, here I'm just express it as an exercise. Assume f belongs to C alpha, 0t, and Rd, such that alpha be larger than 1. Then f is constant. Okay. And by the way, I forgot to tell you, since of course this is the exercise session, feel free to interrupt me anytime. So, okay, yes, this is what we already use it many times. We want to say if we have a Holder function which alpha is secretly larger than 1, then this function is just only a constant path. And this also makes sense, as you know. For example, when we write the Taylor expansion, we always have this kind of expression, t minus s plus blah, blah, blah. So when actually we have alpha is larger than 1, that means this derivative has to be 0. So of course, that means the derivative everywhere is equal to 0. So the path is constant. But okay, just to make this rigorously, the proof is very easy. So assume we just take t and z and t here, and we take two different points here, t. So I just put it, it's assume this guy is 0. So we just implement as many points as here we want to, okay? So I just assume this one be S1, S2, ST, S3, SM, and this guy be SM plus 1. So in that case, by the triangle inequality is less than this one, J between 0 and M Sj plus 1. So by assumption, our path is C alpha for some alpha larger than alpha. So we can say this guy is less than this one. Alpha, yeah. Okay, we can assume, I mean, all this partition. Okay, okay, maybe. So clearly this guy is less than this one. So since here we are free to put as much as the point we want, we can also assume this. I mean, these are all equal. So we can just assume for every I, Si plus 1 minus Si equal to theta. So of course, when m goes to infinity, theta also goes to 0. So then here, we just split it here. We can easily see this guy is less than this one, since size of all of these guys are equal to theta. So, and this is easy. This is alpha minus r. And what is this sum? This sum r is equal to t minus s. And as I said before, theta can be arbitrarily small. So this guy goes to 0. So we are done. This was quite basic, but we will use this exercise many times. That's why I wanted to point it out again. do. The second exercise is actually the fundamental theorem of calculus, but for the Young regime. So I just put it in this way. And it's similar formula which we already observed in the stochastic course, fundamental theorem of calculus. And this is the problem. Assume for two parameters, alpha and gamma, belongs to 0 and 1. Such that we impose this condition, 1 plus gamma be strictly larger than 1, and x be a Holder path and f belongs to this guy. 1 plus gamma. I will define this family as a function. But what I mean with f belongs to C 1 plus alpha, I mean first f is differentiable, and df belongs to C gamma. Then this is the problem. df. F is differentiable and okay, yes, thank you, of course. As I said, we want to say the fundamental theorem of the calculus for the Young regime. Fxt is equal to Fxs. It's similar to the formula which we observed in the last course. Dfxu dxu. Okay, just to clarify everything, what I mean here is this one. I everything's clear? Yes. So just to compare it with the classical fundamental of calculus, in the classical expression of this theorem, we only can assume f is differentiable. But of course here, since x is not smooth, so we have to pay the price. And the price which we have to pay is we need to increase the level of the regularity of the underlying function. So it makes sense. So, okay, so first of all, we want to make sure whether or not this integral is well defined. Solution. Again, feel free to interrupt me. So, first of all, this integral, I mean, defined in the Young regime. We have to make sure this is well defined. So, I just put gamma u be equal to this guy. Then is equal to this point by definition. You want to say something? Exactly. Exactly. I should probably make it more so. Yes, exactly. For young version. For young. And we also have this expression for the rough path theory. It can be generalized. In the second session, I also state another theorem for much singular cases. But this is, of course, the easiest case. Here. This is the assumption. I made it here. Where is it? Here. This is the assumption. Gamma is positive and X is alpha order path, which is satisfying in this condition. So as I said, just try to compare it with the classical case. In the classical case, alpha can be equal to 0. But here, as I said before, since X here is singular compared to the T, so we have to increase the level of the regularity of the F. Correct? Exactly. No, it's more, even more, have more regularity. This is what I want to show you. It actually has alpha gamma regularity. Yeah, alpha gamma. I will show you right now. So again, okay. So we wanted to just make sure whether or not the condition of the Young integral is satisfied here. Remember, we only can make sense of this integral if we have two functions, f and x, such that f be alpha ordered, x be beta, and alpha plus beta be larger than 1. So we want to just to verify the condition of this theorem. So as I said here, df is C gamma, so we can say this is less than x p minus xs gamma. Yep. And what is the regularity of the x? X is also is C alpha. So we can say this guy is less than P minus S, so alpha times gamma became alpha gamma. Correct? So, what was the regularity of the x? This was also gamma. So we can say here, this guy has the regularity of alpha gamma. The x has regularity of alpha. So this guy is alpha 1 plus gamma, which by assumption is larger than 1. So this integral makes sense. Okay, now we wanted to verify this integral, this identity. Okay, the technique is mainly using this simple exercise which I stated earlier. Okay, that means it's enough. P f x u dxu. We want to say this guy has a regularity more than 1. Or more exactly, we will see is alpha times 1 plus gamma. If we just show this guy, then we can apply to this exercise, and we can say, yes, this path is constant, but of course, it has, since it's constant, we just plug t equal to s, then we can say it's equal to 0. So we only just need to show, to verify this condition. Then we can apply, of course, to this exercise. Actually, one of the advantages of using the rough path is many this kind of theorem, which is relatively hard to prove in the classical ethos sense, is much easier since here we're only using some analysis. So here, I just write it here. fxt minus fxs is equal to this one really clearly. Bf xs plus sigma. This is just the fundamental theorem of the calculus. St x st d delta. Correct? So here, put it in the norm here is equal to this one. So I just plug this guy here. Oh, yes, sorry. Sorry, maybe I should say, okay, yes. Delta, thank you. Thank you. And also here. Yes, so we plug it. Sigma xt. We also can insert this integral to this guy. Minus df x times d sigma. Yep. So we're almost done. So by our assumption, it's by our assumption. What was our assumption? We assume the f has sigma regularity. So we can say this guy is less than this one. We just subtract these two guys.
Excuse me?
Sorry.
I don't really understand how you transform the integral between s and t into an integral between 0 and 1 in...
You mean this? You mean here?
Yeah.
Yes. I can tell.
For the second term.
Yes.
The term with df.
fxt minus fxs is equal to this one. The sigma fxs plus sigma st d sigma. Correct? Here? No, again, okay, no, okay. Okay, I see, all right, sorry, thanks. I was a bit quick, I should correct it. You're right, I should correct it here, I was a bit quick. Correct, yep. Let me. I think maybe we even don't need this formula. Yes. Okay. This is less than this one. Fxt minus fxs. We just add this guy. Dfxs. We just add and subtract it. Plus this guy. Now it should be fine. Thank you. Minus this integral. No. Let me just take a look what I've done. Yes. Again, I started version. Sorry. Okay. Fxt minus dfxt, so minus the, oh, it was very quick actually. Again, sorry. Yes, now it makes sense. Okay. So remember we wanted to evaluate the regularity of this guy. So I write it in this way. Fxt, but I will use this identity. Minus fxs. We add this guy. Plus, yes. Minus. S and T dfxu dxu minus dfx delta xst. Now I think this should be fine, correct? Yes, actually, yes. We wanted to evaluate this integral. We evaluate the integrability of this integral. So here I'm just adding this guy and then subtract it here. So then I can here just can in this way split it, okay? So for the first time, what we know for the first time is, okay, it's less than, okay, here we have this expression here, okay, we just plug it here. For this guy, we use this formula here. So I just put it here. Delta xt is sigma minus this guy. Yes, correct. Minus dfx st plus, okay, this was for the first term. And for the second term, I could write it in this way, plus yes, now it's done. Okay. For this term, we just apply this inequality here, which was it here. Okay. So what's the regularity of this guy? So there are, if we just apply this inequality here, so okay, for this term, okay, we know df was gamma holder, yeah. So we can say the first term is less than this guy up to a constant c. So we just subtract them. So xs, these are canceling each other. So the only term remaining is xst. And remember, df was also gamma holder, so it remains this guy. xst. Again, remember, df had gamma regularity. So gamma. And also here, we also have xt here. So in total, it's become equal to 0. And we also here have sigma. Of course, it doesn't matter here. The sigma plus, okay. For this one, we can apply this inequality here. Then what would be here? Since here we are just integrating from s to t, so here we just subtracting the dfx. So remember this guy, this integral was remaining sense. So this guy is in total is equal to t minus s. We show it at the beginning. Yeah, alpha gamma plus gamma. And also, even for same for here, the x was, what was the regularity of the x? The regularity of the x was alpha, yeah? So the first term is also has, so the regularity of x is alpha times gamma plus 1. So both of them has this regularity. So we are done. Alpha, gamma. Here, t minus s. Alpha, this should be alpha, yeah? And also here, I guess. Thanks. So we are done. Yes. As I said, now we just evaluate the regularity of this guy, and we verify this. This integral has this regularity. And the main theorem, the main technique was just to apply in this theorem, which I stated earlier. So. Yes, exactly. It's actually equal gamma plus 1. The regularity of this is actually what we showed it here. Yep. The next exercise is actually the generalization of the Fubini theorem. Okay, again, this is the Fubini theorem for the Young regime. So I just express it this way. Assume again, assume we have a gamma holder. xp belongs to C alpha 0 and t to R. The second assumption is this guy. We can assume we have a family of random function such that for every gamma, y gamma b c beta, and this map is integrable with respect to omega. Omega, so I forgot to say, we have a probability or just measurable set. And alpha plus beta is larger than 1. Okay, these are the assumptions. So we have an alpha holder path. We have a family of random C beta functions such that first of all, this assumption is satisfied, and alpha plus beta is strictly larger than 1. Then this is the Gubinelli theorem, which we want to show. Then EXT. This is the Gubinelli theorem, correct? So it is the Gubinelli theorem in the Young version. First of all, here we have two integrals. We have to make sure all of these integrals are well defined. So, okay, first of all, about this integral. This internal integral is well defined. Why? Since yt is c beta for every omega, is c alpha, and alpha plus beta is larger than 1. So this integral is well defined. So the first integral well defined, but the second integral still we are not sure is well defined. And how about this one? Again, we have to also make sure this integral is well defined. Of course, the first integral is well defined by assumption. It's not difficult, but here is we have dxt, so we have to make sure this integral is also well defined. So this is, I just number it, I, and this is number 2. We want to make sure first of all of this integral is well defined. For the first one, okay. First of all, what we know is, as I said before, this integral is well defined. Is it problem using the green? Or maybe use it. Ext is well defined. Also, again, if we apply this inequality, we know is less than, I just put it, this guy in the other side, y0 omega x st plus the regularity of this guy, a constant, the regularity of this guy, which was beta, and the regularity of x, which was alpha, times t minus s alpha plus 1. So it is integrable. Is it this integral integrable? Is it integrable? Please remember what was our assumption. Yeah? Yes, thank you. Thank you. You know, this is just a constant, so it's not random. So this guy is integrable. These two guys are also constant, and this also is integrable. So this guy is integrable. Yes. Thanks again. Thanks again. Yeah. So we can now say this guy is integrable. Yeah. And also remember to verify this guy also is we don't okay. We so far know this one is integrable, is well defined, and also we want to make sure this integral is also well defined. So we calculate I is well defined. For the second integral, which one? We want to also make sure this integral is well defined. First of all, we start with the internal one. So it's clear this integral is well defined. Is well defined. This is basically this is finite. This, again, you just can't say this is less than y0 omega plus y beta t beta. Again, just apply your assumption. So we can say now this integral is well defined. Correct? It's well defined. So we know this guy is well defined. So now we have a rough path here, and we wanted to interpret this integral as a Young regime. So we have to make sure, since we have to make sure this guy, which is well defined, has the right regularity. Yeah. What would be what we expect this guy, the regularity of this guy? Remember, the x has the regularity of alpha. So we basically expect this guy should basically admit the regularity of the beta. In that case, this integral can be interpreted as a Young integral. So this is a fact. So we are going to compute this guy. So this guy definitely is less than this one. Y beta T minus S beta T d omega. Correct? And definitely this integral is well defined. So we conclude this guy belongs to C beta. Correct? Because of this guy and an assumption. So now we can interpret this guy. We can now interpret all of this integral as a Young regime, as a Young integral. Now again, now we verify which both of these sides are well defined. We want to just make sure these identities hold. And the strategy is same as before. We just subtract these two guys and prove the regularity is larger than 1. Again, we can apply to our first exercise. Okay. So let's compute the regularity of the subs S and P. P the omega dxu minus if we want to show this guy, then we are done, correct? Since remember alpha plus beta was larger than 1, and we can apply to our first exercise, yeah? So we only need to verify this condition. And the trick is not very difficult. We just need to subtract one term, add and subtract one term. We just add this term here. Dxu minus, maybe just write it with another color. This is the term which I'm adding and subtracting. Yu omega PD omega delta XST. So we also need to add it. Here I'm just applying the triangle inequality, yeah? So here I'm just subtracting, so I should now add this term. Yu omega P d omega delta xt. Yep, and also this term. Yu omega dxu p dw. Okay. So I just add this term and then subtract it here. So, okay. And here it should be S, sorry. I'm adding this term. Yes, I'm adding this term. So, okay, now, remember we interpret this guy as a Young integral, yeah? In the first, at the beginning, I showed this guy has the regularity of C beta. So what's happened here? Yes, exactly. Yes, exactly. Again, we are just applying this inequality here, you know? This is actually our path. So this guy is all paths here. I hope everything is be correct. Y omega. I think I missed something here. Wait. Yes, I think I'm missing something here. I also should put this guy. Something here. Wait. No. Maybe I was a bit quick. So again, we wanted to verify this condition here. I should add an auxiliary term here. The auxiliary term is great. This is the right one. It's here, I think. It's, yes. Sorry, it's not correct. I should correct it. I'm sorry. Okay, now it's fine, yes. I'm actually adding this term here. I just put, maybe it was correct. No, I think it was correct. Sorry, it was correct. I'm sorry, it was correct. Y omega, since I want to apply this inequality, so I put it U will be equal to S P d omega delta xt. So I added this term and put it again here. Ys omega P d omega delta xst. Okay. Okay, for the first one, okay. Remember, this is the paths here. This is the paths, okay? And we interpret all of this integral as a Young integral. So we just subtract, we just plug u be equal to s here. So when we plug yes, then we exactly when put u be equal to 0, then we also have the increment. So exactly we are in position to apply this theorem, correct? Exactly we are in position to apply this in theorem. So if we apply to this inequality, the regularity of this part is O t minus s alpha plus beta. Remember at the beginning of the exercise, we showed this guy has the regularity of beta. Now, actually just assume here FUB is equal to this guy, yeah? Just if you want to compare it here, assume this guy be equal to FU. Then what is the FS here? The FS is actually is this one exactly, and this is the agreement which here we also have. So we also verify this guy has the regularity of beta and X has the regularity of alpha. So in total, by applying this theorem, we can say the regularity of this guy is T minus S alpha plus beta. And also for this one. For this one is even easier. So since for this one, we only need to apply the standard inequality in the measure theory. Okay, for the second term here, I mean this guy. Y S omega P D omega minus omega this integral st y u omega dx u p d omega. This guy is clearly is less than this one. Yeah, since this is just a measure or even a probability measure. So this guy is definitely less than this one. So, sorry, something is fine. Yes, exactly. Yes, exactly. Thank you. Exactly, I forgot it. ST. Thank you. Delta x st minus this integral, yeah? P d omega. Yep. Again, we apply this inequality here. Remember here, C is always independent. This is just a general constant, okay? So again, we apply this inequality since this guy is defined in the Rayand regime. So we can say this guy is less than this one. Integral for a constant, the regularity of, the beta regularity of y omega the alpha regularity of the x t minus s alpha plus beta p d omega. Yep. And now this integral is well defined. Why? Why this integral? Why? Again, because of assumption. Yep. So these are the constants, so we can put it outside of the integral, and this integral is well defined. So that shows we also showed this guy is also has the same regularity. Correct? This one?
I think he means on the very
this
left.
one, yeah,
board.
this one. Okay. Okay. You're welcome. Now, as we are applying to this inequality, this is the fundamental theorem which we are applying many times. Okay, so we are applying, for example, this inequality once for here. So this is something which we have just like fu. So here we just subtracting exactly s here. So this is the increment. So we also know this. We also at the beginning of the exercise showed this guy. First of all, is well defined and has the right inequality. So we verify this has this regularity. And for the second time, we also show it here, which again, this guy has the right inequality. Since here, this y omega beta is appearing, which by our assumption is finite. So we can say this is O t minus s alpha plus beta. So again, we are done. We show the subtraction of these two guys is a path with regularity larger than 1. So this guy has to be constant. And since constant, it's not it's not difficult to show this constant is indeed set, is indeed 0. So can I stop another exercise? You have time? 10 minutes?
I think it's already 12, so.
So that we know, yeah? Okay. No, okay, since
I'm not sure how much responsibility.
No, the next exercise is very long, actually. It's the Lyon's extension. It might take 20 minutes, I guess.
But maybe we have at least a few minutes for questions.
No?
Well, if not, then let's thank again Maziar and let's get lunch.
Obrigada. Ahora Chile. Okay. Thanks for coming, and we'll continue with the course of Introduction to Ross-Path Theory. Sebastian.
Yeah, thank you, Solida. Yeah, so welcome everybody to the third lecture. We have the following topics of this lecture. So the space of rough path as a metric space and geometric rough path. Then I would like to talk about controlled path. And the last part will be controlled path as a field of Banach spaces, which is a special structure we found out the controlled path actually have. I have to say that it's a lot of content this time, so I don't think, I'm almost sure that we will not finish today with all these topics. So I think we will maybe start a bit with the third one, and I will continue then next time. Yeah? And maybe just to recall a bit, what did we do in the last lectures? So we started with the theory of integration in the easy case, so where you can use the Young integral. We showed that you can use the Young integral to solve a certain class of differential equations where the driving signal is sufficiently smooth. Then we convinced ourselves that we have to do a very different thing for the Brownian motion. So for the Brownian motion, there is nothing like that easy as the Young integral, as we've seen last time. Then we did I defined a rough path. Yeah, a rough path, if you remember, is basically a collection of iterated integrals or an object that somehow mimics iterated integrals for a given path. Yeah, and then finally, in the last lecture, we saw that we can solve or give a good, write down a good, gave a good idea of what a solution to a linear rough differential equation should be. So we wrote down a series expansion, and we called that the solution. Okay. So rough path as a metric space. So we defined last time this set of rough path, this curly C there. sum of two rough paths. And the reason is simply that when you add two iterated integrals, different paths, this is not the iterated integral of the sum of the paths. So that's not true. Nevertheless, we will see that there is still some structure on the space, and it's still a nice structure, so it turns out to be a metric space of rough path. So this we want to define now. So what you do here is, so given two rough paths, x and y, then you have so the rough path up to, you have the iterated integrals up to a certain level, which is this 1 over alpha Gaussian bracket here. Yeah. So for example, in the case of the Brownian motion, this was just 2. Yeah, and then we take the components here of the path, and we take the differences. So this we can do because these components here, they actually live in the nth tensor power of Rd, which is a linear space. So here you can really take, so we can subtract, so we can evaluate these things and subtract one of the other. Yeah. So this makes sense. It's an element in the nth tensor power of Rd. And then we do something like taking the Hölder norm of this one here. Yeah. So this is something like the Hölder norm. And notice here that we have an n here, which depends on the level. Yeah. Yeah, and then the alpha. But okay, so this is very similar to the kind of norm we introduced for rough path before. Okay, so this is then just something we can define. And it's not hard to see that this is actually a metric on the space of rough path, yeah, because something like the triangle inequality, this just follows from the triangle inequality for this metric follows from the triangle inequality here, yeah, on every level. So this is not much a problem. And furthermore, we can even prove the following. So for any roughness parameter alpha, you can check that the space of rough path equipped with this metric is complete. So it's a complete metric space. Okay, so so this I am not going to prove here, but it's not so complicated. Okay. So if you know a bit about Hölder spaces, then you know maybe that Hölder spaces are not separable. It's a bit like because the problem is that somehow you have a supremum there somewhere. And if there's a supremum, it's often not so good. So also the L infinity space, for example, you probably all know that it's not separable, and also the Hölder spaces are not. So there's no reason why the rough path spaces here should be separable. Yeah, and they are not. So we cannot expect that. But there are often situations where you would like to work with separable spaces, yeah? Especially in probability. You have this notion of a Polish space, a complete metrizable metric topological space, which is separable. So this is a Polish space. And we would like to have something like that also for rough path. In the Hölder worlds, there are so-called little Hölder spaces, you call them. And what you do there is, well, you take smooth paths, yeah, and then you take the closure with respect to the Hölder metric. Yeah, and this is almost by definition then a separable space, which is almost a Hölder space. And you can work with them as well. And there's a similar definition for rough path, and we want to see that now. And this will be the space of geometric rough paths. So what is that? So first we look at the natural lift of a smooth path. So smooth, there are different choices which are possible. So for example, let's take the piecewise C1 functions. Yeah. And then we can define all the canonical lift. We already did that, I think. So we take we take the canonical lift of X to a Hölder rough path. So what we do is we look at all iterated integrals here that are, of course, defined because the underlying, sorry, I should have, what is missing there is continuous and piecewise sequence. So it should be continuous still. Continuous, but doesn't need to be differentiable everywhere. So, okay, so you can define these iterated integrals now, and you can call them, these lifts, then smooth rough path if you want. It sounds a bit awkward, I agree, but let's do that. So this is a smooth rough path, and then what we do, we take the closure of this smooth rough path with respect to the metric I defined at the very beginning. And all elements there you call the geometric rough path. Okay, and indeed what you can prove now is that this space, which is of course a bit smaller than the usual rough path space, is then indeed separable. So in total, this is then really a Polish space. And it has a nice structure. Okay, so now it turns out, so something interesting happens now, that there's also an algebraic structure that is inherited by the smooth path that will also hold for the geometric rough path now. And what is this algebraic structure? Well, what we can observe, for example, when you look at iterated integrals of smooth paths, is that when you multiply two of them, what comes out is a linear combination of iterated integrals. This is not obvious, of course, but so one example would be this very easy, this very easy equality here. So on the left-hand side, remember, it just increments here, xt minus x0, yt minus y0. And when you write down what is on the left-hand side, this you can also, this inner iterated integral, if you want, you can also write as an increment integrating with respect to y, and here the other way around. So when you write that down, it's nothing like so this is what is behind this equality here is the chain rule, I would say. So this holds, so the usual rules of calculus hold here, and you get this, you can easily check that this equality here holds. And, but we've already seen rough paths that do not follow this rule. So, in the stochastic calculus course, you defined the Brownian motion already. Maybe, I'm not sure, you defined also the E2 integral, or you will define that, I'm sure. And then there's the E2 rule, so the Ito's lemma, that tells you that if you take here if you take here the same Brownian motion integrated to each other, then it's not just b2 squared divided by 2, but there's also a correction term here. There's also a correction term. And this is not the same as is written here. So the E2 rough path does not follow this rule here. Whereas we've seen that for smooth path this is true. And so we would like to define, to describe that a bit more in detail. So we would like really to write down what is the product of two iterated integrals. And to do that, we have to introduce a bit more notation. Okay. So we define, again, something like, so you already know what was the extended tensor algebra. Last time we defined that. So and then we had the truncated tensor algebra. And here is actually the tensor algebra. So the tensor algebra is the direct sum of all the tensor powers here. Yeah. So, and I recall that the direct sum and direct product, so the difference is that in the direct sum, all but finitely many entries of this vector here are 0. So this is the direct sum. The direct product, there's not this restriction. Yeah. So this is the tensor algebra, and it turns out that the extended tensor algebra, which is larger, is the dual of the tensor algebra, the algebraic dual. Thank you. Okay, so there is a basis in the tensor algebra. Yeah. So if E1 to ED is the Euclidean basis in the space RD. Yeah. And these tensor powers here are the basis elements in the tensor algebra. And what we can do now is we can identify them, if we want, with words. And this is what I do here. So EI1 tensor blah, 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 EIN will be identified with the word I1 to IN, and where I1 to Rn are letters, so they are numbers from 1 to D, but now I call them letters. Yeah, so I will not treat them as numbers here, but rather as symbols. So it's letters. I will not add, for example, them or something. That's why I will use the blue color here. And then there's also the empty word, so the one that does not contain any letter, and we will also need that, so this will be denoted by epsilon. Okay, so now when I have two words, I can define an object which is called the shuffle product of these two words. Okay, and there's a recursive definition here. So let U and V be words, and A and B be letters. Then, okay, so first of all, shuffling with the empty word, yeah, will not change the word here. So that's what the first line says. And then the second is, so it's recursive, so it assumes that you already know what is the shuffle product of this word here and this word. So and then define it by exactly this one. So okay, what does this here mean? Just putting the A on the right. This means you concatenate. So you just add the letter from the right-hand side to this to every word in this sum. So this is the sum of words. And here as well, so you add a letter B on the right-hand side to this to every word in the sum. Yeah. Yeah.
On the right-hand side, the first A is following U, right?
Yes. Thank you. Yeah, this should be a U. Absolutely right. The rest is, I hope is correct. Okay. So. Epsilon was the, sorry? The empty word, yeah. So what was, how to control L? Okay. Thank you, yeah. Okay. Okay, so you can shuffle two words, okay? And what comes out is not a word, but it's a sum of words. You know, it's a sum of words. And okay, so what we define, so words are actually basis elements in the tensor algebra. Yeah. So and an element in the tensor algebra is actually a sum, well, a finite sum of these basis elements, with some coefficients in R, of course. So we can identify them then with the sum of words with some coefficients in R. Yeah? And for these elements, we can also then define the shuffle product here by just extending what we've just seen by linearly. Yeah? So the shuffle product should be bilinear. And then we defined it for, indeed, for every element there. Okay, so this was the definition, the formal definition, but I think you learn best what it means with an example. So it's really like shuffling cards. That's why I put this picture here. So you start here with 1, 2, and 3, and then you look at all combinations putting the 3 in this word here, 1 and 2. So the one possibility is putting the 3 at the very end. One possibility is putting the 3 in the middle, and another possibility is putting the 3 in the very beginning. But the rule you have to follow is that you are not allowed to change the order of the letters in these words. So the 1 has to has to come before the 2 always. So this was one example. Let's look at another example here. Here 1, 2, shuffle 2, 4. So you have two decks now, and then you look at all combinations of putting these words together, yeah. But they have to keep the order. So the 1, 2, 2, and 4, they always have to be in the same order. But what happens now is that for 1, 2, 2, 4, you have the 2 in the one word and the 2 in another word. And so one combination would be you have the first 2 here and the second 2 here, but another combination would be you have the first 2 here and the second here. Yeah. So this appears twice, and that's why you get a 2 here, yeah, because you have 2 times this word. And here I wrote the 2 in black because this is the number 2, really the 2 in the real numbers. And then all the rest. Okay, so this is the shuffle product. So let's look again at a smooth path now, and let's look at as the collection of all iterated integrals. So an element now in the extended tensor power, the extended not tensor power, sorry, tensor algebra. So with the notation we introduced, we have then the following. Okay, remember that 1, 2, 1, we identified with the basis elements. So this would be E1, E2, tensor E1, tensor E2, tensor E1 here. And here bracket means really I apply, so the left-hand side, the tensor product is dual, the tensor, how was it called, this object, sorry. So let me go back. Tensor algebra, okay, yeah. So the tensor algebra is dual, the extended tensor algebra is the dual of the tensor algebra. That's why I use these brackets here. Yeah? And so if I evaluate this, so then I get exactly this iterated integral here. So dx1, dx2, dx1. So I also can look at the linear combination of words here. So then this would be square or the root of 3, square root of 3, times this iterated integral minus 2 times this iterated integral, and so on. Yeah? And so on. And then you have this very nice theorem which tells you the following. So I can now, so what is written here on the left-hand side? So here I take elements, so like sums, linear combinations of words on the left-hand side. I evaluate it So what I get is a linear combination of iterated integrals here as well. And then I multiply them. So this is then really a multiplication just in the real numbers. Yeah. And this is then the same as taking the shuffle product and evaluating them. And this tells you exactly with this formula, you can use now really to say what is the product of two iterated integrals. You can use it to calculate the product of iterated integrals, and what will come out is a sum of iterated integrals again. Okay, so I wanted to show you that. And so this was true. This was true for a smooth path, so for a lift of a smooth path. But this is now inherited also by geometric rough path, because geometric rough path where basically, yeah, you can approximate every geometric rough path by a smooth rough path. And since smooth rough path follow these rules, it's also true for geometric rough path. Okay, so let's take it. This is the corollary then. Let's take a geometric rough path. So we identify it now with, given by the lines extension theorem, to an object with values in the extended tensor algebra. And then exactly the same thing here holds. Yeah. So in particular, we've seen that the Brownian motion, the Ito lift of the Brownian motion, although we defined it to be a rough path, it's not a geometric rough path because it does not follow this rule here. Okay. Okay, then we can define also an object. So it often appears in the literature. I will not need it in this lecture, but I wanted to define it nevertheless, maybe because you heard about it, which is the signature of a path. So the signature of a path is, so you can even take a rough path here. So you take a rough path and then extend it with the extension theorem to an element taking values in the extended tensor algebra. And now, but now what you do now here, this is a different thing to rough path, you fix 0 and t. So you do not look at, so this is not an object defined on the, having two unknown, so two arguments. This is not a function with two arguments, but to fix 0 and t here. So this is really just an element, it is an element in the extended tensor algebra. It turns out that this element, it's infinite dimensional, but contains a lot of information about the path, about the rough path. So there were a series of papers. I think the first one was Chen, so quite old paper, and then other people, so Terry Lyons, Ben Hembley, and finally there was a paper, the very general one, which dealt with rough paths. So Chen started with smooth path and so on. And what they showed is that the signature, so this object, this infinite dimensional object, from this object you can recover the path, the underlying path, up to certain property that is called tree-like excursions. Yeah. So what is a tree-like excursion? So I just draw a picture. So when you have a path in R2, and what can happen is that the path goes here, but then goes back exactly here, so, and then goes on. Yeah. It goes in one direction here, but then goes exactly back here. So this would be a tree-like excursion, and in the signature you cannot see that tree-like excursion. Yeah. So without this tree-like excursion here, the signature would be the same. Yeah. So and when you remove all tree-like excursion from the path, but this then you can recover from the signature of this path. And also you don't see the you can reparameterize the path also, and I think this also doesn't matter. Yeah? So you will not see that. But yeah, this is not, of course, not trivial. And so this gives you a way somehow to store important information of the path. And you can now say, okay, so when I draw a path, or if I observe something, what is the essential things of this path? And one possibility would be that I say, okay, let's look at the first nth level of the signature of this path. Yeah, since I know that if I look at every level, I can recover the path. Maybe the first n, if I choose n large, is already a good somehow approximation of the features, the important features of the path. And these features then you can try to learn. And then, and that's why this truncated signature or the signature plays an important role in machine learning. People used it in machine learning. Okay, so this was all what I wanted to say about the signature. Now there's, of course, the question, well, the Ito rough path is surely not geometric. But what about the Stratanovic? What about the Stratanovic lift? So the Stratanovic lift, for the Stratanovic integral, you have the usual rules of calculus. So the Ito lemma, there is no, this correction term does not appear here. So there is at least a chance that the Stratanovic lift of the Brownian motion is indeed, so it's almost surely takes values in the space of geometric rough path. And this is indeed the case. And this is what we want to prove now. And remember, we have to prove now that every trajectory is actually can be approximated by a smooth path. This is what one has to prove to see that. So let's do that. So for simplicity, t equal to 1 will not matter. It just simplifies a bit the notation when we do that. And yeah, so what we do is, given an alpha here, we can choose an alpha prime, which is a bit larger than alpha, but still less than 1/2. Okay. And then we know also from the Kolmogorov-Chantsov theorem. Okay, so this is an object only in having these two components. So here only the second iterated integral plays a role. So we can take the alpha prime norm here, and from the Kolmogorov-Chantsov theorem, we know that this is finite almost surely. I forgot to write down here. Okay, this is finite almost surely. Okay, so now we take piecewise linear approximations of the path at the dyadic points. So in one dimension, if you have the dyadic points here, and then you have your Brownian trajectory, piecewise linear approximation would be just that one, yeah? Okay, and this is smooth. This is then smooth in our how we define smooth. So because this would be piecewise C1, right? Continuous and piecewise C1. So what we can do now with this smooth path, we can look at the lift, the canonical lift. So we lift this Bn to both Bn to an alpha Hölder rough path. It's of course more regular, but we want to consider this topology because we want to prove now convergence exactly in the alpha Hölder topology. Okay. Okay, so now we do something we already did for the Brownian motion. So we look at increments here on the nth level and bound the L2 norm. Yeah? And then we have something like for the Brownian motion, this can be bound by t minus s to 1/2. And in the second level can be bounded by t minus s to the 1. Yeah? Exactly like for the Brownian motion. But here's important, so we do not have a stochastic integral here, but a pathwise defined integral. But okay, can do the same. And what you can prove, what is important here, that the constant on the right-hand side here does not depend on n. So there's a uniform bound you can obtain, independent of n. Okay. And now you use again that the process, that the Brownian motion is Gaussian. And this tells you that this estimate holds actually for in the AQ norm, so for every moment. The price you have to pay is just that the constant might get larger here. The C gets larger, but it's okay. And then you use the Kolmogorov-Chentzov theorem, the one I wrote down, and this tells you that, okay, this norm, this rough path norm here is finite in alpha prime. Yeah, also for alpha prime, but uniformly now. So you can use the Kolmogorov-Chentzov theorem here to get a uniform bound for this natural or canonical lift of the approximated Brownian motion in alpha prime. Okay, so now it's come something that's maybe a bit quick, but I claim that to prove that this is what we aim for, by the way. We aim to prove that these approximations here converge to the Stratanovic lift of the Brownian motion in alpha Hölder, the alpha Hölder metric as n tends to infinity, because when we proved that, we proved that the trajectories, so when we proved that this holds almost surely, of course. When we proved that, we've shown that every trajectory of the Brownian, of the Stratanovic lift of the rough path can be approximated by a smooth rough path. So this is what we aim for. So we know that this norm here is uniformly bounded, and I claim that by the Arcela-Ascoli theorem, it is sufficient to prove that Bn converges to B, and also the iterated integrals converge to the iterated Stratanovic integral only pointwise as n tends to infinity. So this is a bit surprising, maybe. So uniformly would be then clear, but to prove that it's to see that it's only that pointwise also is sufficient, this follows from the Arcela-Ascoli theorem. Okay, so the first statement is actually clear, or say basic. So you can just calculate. So you just have any continuous function, you approximate it piecewise linear, and then when you let the when you let the mesh points here get smaller and smaller, they converge pointwise in this approximation. So this is not complicated. What is more complicated is the second level. This is what we want to do. And there's also an easy part, namely when you take the same Brownian motion in the integrand and in the integrator. Here's a BI, and here you also have BI. Then you have the Ito formula for the Stratanovic integral that tells you that this is just here the increment of the Brownian motion squared divided by 2. And so then we already know that this goes to the Brownian motion, which is then again the Stratanovic integral. So this is also easy. So the only thing we have to, or what remains to show now, is that this also holds here if the I, here's an I and here's a J, when I is not equal to J. Okay. Okay, so now we define a fit. So we define first here a sigma algebra, so generated by the BK, where we evaluate the Brownian motion. So these are exactly the random variables where we evaluate the Brownian motion at the dyadic points. Okay. And so remember, since we used the dyadic partitions, this is a filtration because the points are contained. So when I have a finer one, then the points are also contained in the so the points before are contained in the finer one. That's why I have a filtration. I need that now. Okay, so now you make a calculation, and there's a nice thing, this is a nice exercise to do. So now condition your Brownian motion on this filtration here, and what comes out is exactly the piecewise linear approximation of the Brownian motion. This is true for the Brownian motion, by the way. It's not true for the fractal Brownian motion, for example. So you need specific properties of the Brownian motion. Okay. Okay, so what we have here is a Martingale. So what we have here is a Martingale on the right-hand side, and you can prove that the conditions of the Martingale convergence theorem are actually satisfied, so that you can prove that the BTN converges to this, converges for n to infinity to this random variable here, which was the Brownian motion evaluated at t. Almost surely, and in LP also, but what we need is almost surely. But this we already know, yeah? This is just a complicated proof, if you want, of something we already know. But the nice thing is that exactly this reasoning will now work also for the second iterated integral. So for I not equal to j, so what do we do now? For I not equal to j, so here you have to believe me that when you look at these iterated integral here, then this is a sum of, this is actually, this can be written as a limit of Riemann sums here. Why does it work here? Well, this works because I is not equal to j, and bi and bj are independent. That's why that works. Otherwise would not. Okay, so you can do that, and you can also interchange limits and all that, okay? And then, and then you have, again, a very similar situation as before. You can use Gaussian conditioning. Of course, I do not the whole calculation here, but what comes out here then at the end is that it's exactly, again, a Riemann sum here. So here I forgot the limit, sorry. So here I forgot the limit. So you take the limit again, and what comes out here is then really this lift, this natural lift of the approximated Brownian motion. You have the same thing as before. So we can apply again the Martingale convergence theorem, and which shows you that this indeed converges almost surely in LP for any p, and this, I told you, finishes the proof. Okay, there's many details left, but I think you can work on them on your own if you like, so that's why I said it's a nice exercise. Okay, I should say that there are also other proofs for the Brownian motion which are different, but I think this is a quite nice one because it maybe uses things you've learned in the stochastic calculus course, like the Martingale convergence theorem. Maybe I should say here, the Martingale convergence theorem, I use the discrete Martingale convergence theorem, not the continuous one, really for n to infinity, because I fixed the t. And there's also a thing where you have to be careful when you work, if you really want to work out here. For every t, I have a convergence almost surely. So that would mean that for other t, I have another null set where this maybe does not converge. Yeah. But you can use the continuity here to find a set with full measure where you have the convergence everywhere. So, okay. Okay. So that's what we did. So we defined a geometric rough path now. We saw that at least one of our lifts of the Brownian motion can be lifted to a stochastic process that has trajectories in the space of geometric rough path. So now comes a very important next chapter that are controlled paths. So I think we have a question.
Why is it called geometric rough path?
It's a good question. So this is how it was introduced, so how people call it. So I would say that somehow it's because it's yeah, it follows the usual rules of calculus. That's why I would say. So it's somehow the natural thing you would expect. But I don't know. You can ask Terry Lyons that if you want, because he introduced this. Okay, so controlled path. So our goal in this lecture is actually to solve rough differential equations, so equations driven by rough signals. And so we already can somehow write down a solution to a linear rough differential equation, but what we cannot do yet are nonlinear equations, so equations like that. We saw in the Young case that it's maybe a good idea to interpret this equation as an integral equation. No? So maybe there's a good notion of an integral we can use here. Of course, it's a bit complicated. So, yeah, we had this meta theorem that told us that this is a challenge. Yeah, but let's see what one can do maybe. So it's natural to what we want that the integral should satisfy here is that coincides with the maybe e to integral if the f here, if the function here happens to be smooth. Yeah, so this is something one would like to have from an integral. And what we also would like to do, because we've seen that it works very well in the Forhölder equations, what we would like to have here is that if we integrate a function, that then also this element on the right-hand side where we vary the t should be again in the same space, in this Banach space. So what should this Banach space satisfy? It should contain smooth functions and should coincide with the usual integral here. And this map here should exist and should be continuous. And this, okay, and okay, and this cannot hold. Yeah. So one can show now that these conditions contradict each other, so this space does not exist. So you've seen something like that before. So this is here I call it Theorem 51. So there is no space of functions E carrying the Wiener measure. So remember, carrying the Wiener measure was something like it's large enough such that you can define a Brownian motion on it. There's no function carrying the Wiener measure on which you can define a continuous map I that coincides with the pathwise defined integral here for smooth function on a set of full measure. Continuous is important here, continuous map. And the proof is basically the same as we've already seen in Theorem 24. Okay, but what is now the solution? Well, one solution is, or one thing is that we asked for is that we have a fixed space, a fixed Banach space on which we want to define that map. Okay, but we want to establish now a pathwise theory. So what we can do now, at least in principle, we could allow that the space itself will depend on the trajectory of the Brownian motion. And indeed, we will define now spaces that will depend on the rough path, but on which we can define this integral map here, and it will be a very nice map. So in particular, it will be continuous. Yeah? It will also coincide with the integral on smooth paths. Now, but the price to pay, we have to pay now is that we let the spaces on which we define this integral map here will depend on the rough path, or later when we use it for the Brownian motion, will depend on the trajectory of the Brownian motion. Okay. Okay, so our goal is to define this rough integral for a given rough path x. And okay, now I restrict myself to, so before I always looked at every Hölder parameter, but now I want to restrict myself to alpha between 1/3 and 1/2. But remember, this is already good enough for integrating the Brownian motion. So somehow this is, the interesting process is contained here. And yeah, so remember in lecture 2, maybe, in lecture 2, what we also had a look at this iterated integral here was a smooth one in lecture 2, but to deduce the right regularity at that time, to deduce the right regularity of this 3 times iterated integral, we wrote down, we wrote it down as a, not only as a limit of Riemann sums here, but also we had somehow a compensator here on the right-hand side. Yeah, and this compensator was really important to deduce the right regularity. I mean, you can redo the calculations if you want without, and you will see that you will not be able to deduce the right regularity. So the idea would be now, well, that we do the same somehow. So we do not look only at Riemann sums here, but we also assume that there is some object, I call y prime here, that has to have certain properties, of course. We will see what kind of properties this object should have. And then maybe together with this compensator, we can define this, this integral, this rough integral here. Okay. So the new thing is that we assume that there's some y prime here. Okay. So what should this y prime satisfy? Yeah. So, of course, our main tool always was this Turing lemma. Yeah, this is also what we used to deduce the right regularity of these iterated integrals. So let's define this psi here together with this compensator. First thing you observe is here that this psi itself has an alpha Hölder regularity. Yeah? This is just because the x here has this alpha Hölder, and the this second order object here is also alpha Hölder. It's even 2 alpha. Okay, so this is already good, but of course the crucial thing is here the regularity of the delta psi. We have to prove that this is true for some beta larger than 1. Okay, so I assume maybe also in the exercise sessions you did these calculations already with the delta operator here, so you can do the calculations here as well, and what comes out is this identity, if I didn't make a mistake. So here you have this this term here, and then on the right hand side you have this term here. Okay. So we arrive now at the following conditions. So we want this to be beta Hölder for some beta larger than 1. So to obtain that, we would need that the first term here is together has a regularity of a beta larger than 1. So this has a regularity of alpha. Yeah. This has a regularity of alpha. So, okay, I'm in this line here. So this thing here, so this object here needs to have a regularity of gamma tilde here, such that alpha plus gamma tilde here is larger than 1. So this was only this term here. Okay, what do I need here for this term? So I know that the bolt x here has already a regularity of 2 alpha. So the alpha, so the y prime here, the y prime needs to have a regularity of gamma, such that gamma plus 2 alpha is larger than 1. So these are the 2 conditions. Under this, if I knew that, I could apply the Turing lemma. So in particular, this is satisfied if I choose the gamma equal to the alpha and the gamma prime equal to 2 alpha, because the alpha was assumed to be larger, strictly larger than 1/3. Then this works. And this is what you now use, and you make the following definition. Okay, so you fix a rough path, and then you call some alpha Hölder path controlled by x if there is some sort of derivative such that the remainder term here, so the derivative should be alpha Hölder, yeah? And the remainder term here, given by this, should be 2 alpha. Yeah? And by the way, this should remind you maybe a bit of the Taylor expansion here. But so what you have here is somehow you Taylor expand that, but not somehow in time, but in the rough path. So you replace t minus s by the increment xt minus xs. Okay, and there's also a name. So since Gubinelli introduced somehow this, at least in the book of Peter and Martin, they call this y prime a Gubinelli derivative of y. And then we can define the set of controlled path. This is called, so we use this D here. This is a set of pairs. So you always have a path together with a derivative. Yeah, and we define a semi-norm on it. So it's defined like that. So you take just the alpha Hölder norm of the prime and the 2 alpha norm of the remainder here. We could ask, why is the alpha Hölder norm of y not included here? This is just because you would like to be a bit economical, so you can bound the alpha Hölder of the y here by this quantity and the alpha Hölder norm of the x. We will see that also later. That's why you do not want to include it here. Sometimes you can do that also, but wouldn't change anything. Okay, now remember I told you that the space of rough path is not a linear space, it's a metric space, but the space of controlled path is actually a linear space. So you can add 2, so you fix a rough path, and when you have 2 controlled paths, you can just add them and subtract them and multiply them with scalars. That's okay. And it's not only a linear space, but with what I defined here, it's even a Banach space when you do not look only at the semi-norm here, but also take into account, say, the initial condition, so the initial value of the y and the y prime here. Then it's a genuine norm, and you can prove completeness of these spaces. So the thing is, I always said there is a Gubinelli derivative, and this was for a reason. So other than for usual functions where the derivative is unique, if it exists, this is not the case here necessarily. So there can happen that the path has actually 2 derivatives, 2 Gubinelli derivatives. And it's not hard to see that. For example, we can assume that x is smooth. Yeah? So let's look at again at the condition here. So this should be 2 alpha. So not x, sorry. If the y is smooth, here, we could take y prime here to be 0. Because then, so smooth, I mean at least 2 alpha. So then this would be okay. But actually, if now x is smooth too, we can choose any C alpha path as a Gubinelli derivative. Because so if the y is smooth and the x is smooth, so at least 2 alpha, then it doesn't matter how I choose the y prime here. Interestingly, I do not do that, but interestingly, this is the only thing that can go wrong. So then we can prove that if you have a genuine rough path, so a truly rough path, it's called, then the Gubinelli derivative, if it exists, is unique. But we will not do that. Okay, so we introduced controlled path because we wanted to define an integral. Yeah? And this is what we want to do now. So controlled paths are good integrals. So this is the theorem. So let's take a rough path. Let's take a controlled path, the controlled by this, by x. So, okay, so I do something here which is maybe should be a bit careful. Sometimes I use bold x, sometimes I do not use the bold x. And by that, I mean just the projection of this on the first level. Yeah. Because remember, we had a rough path, but a controlled path in the definition, only what was needed is the first level. We didn't need actually the whole rough path. So let's take a rough path and a controlled path. Then the integral here on the left-hand side indeed exists as a limit of these Riemann sums plus this compensator. And moreover, it satisfies a certain bound here, integral minus this one, where here, okay, what you see here, you see the alpha Hölder norm, you see the 2 alpha Hölder norm of the second order object, and you see the remainder and the alpha norm of the y. And then t minus s here. Yeah. T minus s, sorry, to 3 alpha, that's important, 3 alpha. Okay. Okay, and what you can also prove, this is also something we wanted to have, if you remember, to perform later a fixed point argument, we want that the integral here is again controlled. Yeah? So if I vary the upper argument here, the t, and this is a path which turns out to be again a controlled path with a Gubinelli derivative, a y, yeah, this one. Okay, so I have now a map. I have a map here from the space of controlled path. So I can construct this map to a space of controlled path. So it's a bit different here because this here lives in another, so it takes place in another space. So these are the linear maps here. This is just Rm. But still, it's a map from space of controlled path to another space of controlled path. And this is a continuous linear map between these spaces. And moreover, we have this bound here. Okay. So that z here is is the right-hand side. So it's the rough integral. Okay. So say again, please.
Z prime really coincides with y, so the coordinate there to be y.
Yes, z prime really coincides with y. Yeah. Z prime is y.
I see, because the definition of this graph is where you need y prime, right? That's kind of hidden there.
Yeah, and so you need the y prime to define that. But yeah, so it's there. Okay, so what is the proof? Well, the proof now is actually quite easy because we constructed these. We already did the calculations, as you remember. We constructed this controls path exactly that it works somehow. So we use the Turing lemma with this. We make this ansatz here for the psi. And then we do the calculation. We already did that, if you remember. So here now I have the remainder term. And so we see that indeed we can bound the delta psi norm, 3 alpha norm, by that one. Yeah? And this is already it. So this already shows that you can apply the Turing lemma, and then you could define also this limit there existed. Okay, the second one was to prove a bound. Now, the second assertion was that we wanted to show that this is again a controlled path. Yeah? And so why is that? Well, you look at the remainder. Well, first of all, it's easy to see that what was the derivative? It was just y. So this was assumed to be alpha Hölder, so this is clear. So what we have to check now is not that Z prime, so we saw that Z prime has the right regularity, but what we need to check now is that the remainder of Z here is actually 2 alpha Hölder. So what was it? So we plug it in, so we see that it's exactly that one. Yeah? Okay, but we already know this bound here. We already, oh, where was it? Sorry. This was the first assertion. We already know that bound here. Yeah? This is what we deduce. This comes from the Turing lemma for free. And this, what is written here is exactly where we want to deduce the 2 alpha Hölder regularity. Yeah? To deduce the 2 alpha Hölder regularity of this, what we do now is just we add this term, we subtract it. Yeah? So then we use the 3 alpha Hölder regularity of the first term, and this alone here is also 2 alpha Hölder. Okay, so in total, we see that this term here is also 2 alpha Hölder. Okay, and the rest is actually also not hard. So you calculate the bound for Z and Z prime here. So you just plug that in. What was Z prime? It was just Y. You calculate here really the bound again with the triangle inequality, and what comes out is exactly that bound I wrote down. Yeah. Okay, that's it. Okay, so I'm faster than I thought, so I can talk also a bit about the controlled path as a field of Banach spaces now. Okay, so what did we do? So we defined for every rough path, or say for every Hölder path, a space, a Banach space, yeah, which is the space of controlled path. And the question is now, okay, I have all these spaces, but do I have maybe a bit more? Do I have a bit more structure? Can I say something about these spaces altogether, or are they just isolated spaces that do nothing, which are just isolated? There's no common thing I can say about all of them together. And yeah, so this is of course a natural question, maybe a theoretical, but maybe natural question, but there's also some relevance, some practical relevance around that question. So recall that for rough integration, what was rough integration? So rough integration was a linear map, so a continuous or bounded linear map between 2 spaces of controlled path. Yeah? So for every bold x, you had a linear map. And okay, in many situations, this x here is random. For example, it's a Brownian motion. Yeah. And what you can do now, okay, for every rough path here, for every fixed rough path, you can look at the operator norm, which is that one here. But if the space, if the process happens to be random, then you have somehow, yeah, so then you have for every omega, you have another trajectory, so another space. So on the right-hand side, this would be a random number. Yeah. So the operator norm here on the left-hand side is, first of all, is a natural quantity, I would say, to consider. It's a random one. And one seemingly very basic question here is to answer, what you want to answer first is the measurability of this random number. But I don't know, but when you see that, I don't see why, a good argument why this should be measurable. Yeah. And we will see that having this additional structure I'd like to talk about now will actually give you a way to answer these kind of questions. Okay, so we make a following definition. So this can be found in the literature. It's quite old one. A field of Banach spaces. What is that? Okay, so we have a topological space X. So in our example, this would be the space of rough path. And then for every x here, we have some linear space. So we have a continuum of linear space. Okay, and we call this a separable continuous field of Banach spaces if there is a countable set of sections, delta. So what is a section? A section is a map from X here, well, first of all, to the union of all these Banach spaces. That has the property that if I take an X here, so this would be the Banach space indexed by this element. So a section would be, I take this element and I obtain an element in this space. Okay, so this would be a section, and if there exists a countable set of sections that has two properties, I will call that a separable field of Banach spaces. Okay, separable is of course because of countable. Okay, the first condition is that if I fix the G, if I fix such a section and I look at the mapping from X to G of X, so what is this element? This would be an element in EX. So I can take the EX norm, then I have a real number. So this I want to be continuous. Okay. And the second thing is here I do not fix the G, but I fix an X now. I fix an X, and then I look at the set that runs through all these G's in the delta. So that all points then here in the space. And what I want is that this set is dense in the space EX. Okay, I can ask for that as well if I want. Yeah, so this is what is called a continuous field, or I call this a separable continuous field of Banach spaces. Okay, so when you have a look in the literature how people define this, this structure, it's a bit different sometimes. I want to mention that here. So for example, we also always had to look in this Dixmier book. So first of all, they assume that there is a linear subspace of sections. Here I call it delta prime, satisfying 1 and 2. So I only assumed that it's a set, countable. And separability would just mean then that there is a subset of the section satisfying these properties I just told you. Yeah. But I would say that it's clear that how I defined it would also yield a continuous field of Banach spaces in this, like in this book, because you can of course just look at the linear span of this delta and you obtain the delta prime that satisfies these properties. So it's okay. And another thing is there's another property Dixmier assumes about this set delta prime. It looks also a bit, well, you have to get used to it maybe a bit, but you can draw a picture here. So let's assume that we have some section, so not an element in the delta, G tilde, which has the following properties. So we take some section here, and then you have maybe a fix Y here, and okay, so you fix an epsilon, and okay, so what's, you fix a Y, you fix an epsilon, such, and if there is now an element G Y such that in the neighborhood around Y here, okay, so here you have all these spaces and the G tilde here gives you points here, maybe G tilde, here, G tilde, so. And if there is an element in now the delta prime space such that in an epsilon neighborhood the image of gy here lies in this neighborhood, if there is such an element, then we already know that the G tilde is also an element in here delta prime. Okay, so this is maybe not so easy to digest, but fortunately one can show, and this is done in the same book actually, that if you have a delta prime setting satisfying only the conditions I wrote down in my definition, and that you can do some sort of completion. So you can make your delta a bit larger, such that also this property will hold. So it's no restriction. So definition I gave you is actually no restriction. Okay. So if you want, you can call this then a pre-field, so to make to show, to make it different. And the question now is, of course, do we have such a structure for rough paths? So do the spaces of controlled path, do they have such a structure? And it turns out that this is true, but a slightly weaker result is true. But so we will formulate that now. And we will make another definition now of controlled path, which is a bit similar to this definition of geometric path or the little Hölder spaces you've just seen. So we take now a closure of smoother path with respect to another metric. Okay, so let's fix a rough path X. Let's fix two parameters. So another parameter alpha here. And this space will be then the closure of the space of controlled path with the alpha norm. And alpha was less or equal to beta. Okay. Okay, having these, so they are also separable spaces, by the way. I don't need that, but if you want to work with separate spaces of separate controlled path, you could work with them if you want. And then we have this lemma, which is the core of the proof that we have the structure of a separable field. So what does this lemma tell us? Okay, so you have actually now three parameters. So we can be generous. So take an X with a gamma regularity, take beta less or equal to gamma, and then take alpha strictly less than beta. And then you look at the following set. So it's a set of pairs also. So Z, T is a path here where you integrate a smooth function with respect to X. And then you add another function, which is also smooth. And the Z prime here, S for the derivative, is just what you integrate. So the integrand here. So the phi also. Okay. And what the lemma tells you is that this set here, it actually, these elements here are controlled paths, and they are dense in this space. This also gives you a quite nice description, I would say, at least of a nice set inside the space of controlled path, which is very explicit. And the integral here, yeah, you can ask how is it defined. But this is not a problem here because the phi here is as smooth as you like, so we can define it as a Young integral. Okay. So this is so this now will be a bit, I think the last thing we do today is the proof of this lemma. Oh, let's see. Okay, so what do we have to show? Well, it suffices by definition to prove that Z here is dense in the d beta space, equipped with the alpha norm, by definition. since this was just a closure. So let's take an element here so an element of control path with some remainder. So what do we know? We know that the psi prime here has finite beta norm, and the remainder has finite 2 beta. So we take a partition. So we will also we construct somehow a piecewise linear approximation to this control path here. So we take a partition. This time we do not need somehow that this is a dyadic partition, so just take any. Okay, here we assume for simplicity that's a uniform partition. So the size of 2 points here will be next to each other is theta. And so we approximate now the Gubinelli derivative, piecewise linear. So we take a piecewise linear approximation with respect to this partition. So you can write it down like that. Okay, and our goal, so we would like to find a function. So this is the definition of the psi bar. So we defined approximation to psi tilde here, psi bar tilde, and we want to define psi bar as follows. So we integrate this piecewise linear approximation here and add a smooth function. Okay, the smooth function we still want to define, so it's not clear what it is, but what we want is that this converges in the norm on this space here, which is the same as the semi-norm, because the initial conditions are equal in alpha Hölder topology to 0 when I let the theta, so the mesh size I started with, and if this is small. Now, this is what I want to do. Okay, so there are 2 things I have to do. So first of all, I have to prove that these here, they converge in the alpha Hölder norm. And so we give that a name here for later purposes, but we will not prove that here. So we give that as an exercise. But what is important here was that we knew that the psi prime here was in the alpha, in the beta Hölder space, not in the alpha Hölder. Otherwise, this would not hold. So this is a weaker topology. Okay. So it remains to show that also the remainders here converge in the 2 alpha Hölder topology as theta goes to 0. And this was the remainder, just to remind you. Yeah. And still, what we did not define here was the psi, so it's still not chosen. Psi, sorry. Still not chosen. So let's introduce another object here, which is then, actually this minus that one, we give a name, namely we call this rho st here. You can also put it inside the integral if you like. It's the rho st. And okay, what do we know now? What do we know now? Well, we know that the psi bar prime here was a piecewise linear approximation of the psi prime. So that means if I take now S and T inside 2 points of the part, so 2 neighboring points, then I can write down, so I can put this out. So this was, here I just used the definition of what is a piecewise linear approximation. So I have what's left with this integral here. And this integral now I can bound, with, for example, I mean, you can also do it in other ways, but we can use also our bound for the Young integral to see that this element here can be bounded in the 2 alpha norm bounded by this one here. Okay, this is maybe not so immediate for you. You have to calculate regularities, but this is what comes out. Okay. Now we take any partitions, so any points in the partition, Tj, Tk, and P. And okay, so the definition of the rho, if you want, you can recall if you want on the slide before. And here you use the linearity of the integral. So when you have a long one, you can chop this integral up in small integrals and take the sum. And you do some calculations here. I cannot do all of them here in detail now. But what you end up with is then this element here. So what you should remark here is that here I add up small partitions, and here I have the remainder of this is a large partition. So tk and tj are large, maybe away from each other. Okay, so this is terrible. What was it? Control L? Yeah. Okay. Okay, so now I'll make another definition, the row tilde here. It's like the row before, but I subtract or take minus row minus what is left here on the right hand side. Yeah? So this term. Okay, and then the calculation, what I just did is exactly that I can say, okay, the row prime, tk, tj, then I only have the sum of these elements here, the small increments somehow. Okay, so now I define psi tilde to be the continuous piecewise linear function having these properties. So first of all, it should start in psi 0. And on ST between these 2 points, the increment should be exactly that one. Yeah? And by these 3 properties, this function is uniquely defined if you think about that. So these are the properties I need. Okay, so with this choice, okay, so with this choice, yeah, so this was the choice. Okay, this is, yeah, now there was the definition of the psi, no? So this was the definition of the psi. I call it here psi tilde because it's not smooth. It's the only thing, it's the only difference. But it's piecewise smooth. So at the end, it will not be a big problem. Okay, so now I have the definition here. So I have that one, and if you have a look, what was the definition? So so this was just the row st plus delta. So yeah, so it's like that. So for this psi tilde here, these objects here I know quite well how they behave, and I can now look at S and T somewhere in the partition. Somewhere in the partition, so it can be far away from each other, and then I can write it down as, okay, a smaller one, small partition, tk plus 1, and so on. Okay, this is because, well, this is just additive because this was a function. Okay, it's just a function. Okay, and then I can also write it down like that if I want. Now I have, I used the 2 before, so I think I will not go through all of that here if you want to read it up. You use another direct calculation of the row here. It's a bit like these calculations you perform with the delta operator, what you need here. For the row, you can do some calculations for the row prime as well. And what is now important here is if I take the difference, between these 2 here, it turns out of all these, when you plug that in, what is important here let me see, is that I have only increments here of, yes, no, here. So, no, it's fine, okay. So if you see, I have only increments here that are small. So there's no increment containing tk plus 1 tj. No, it's no. Okay, maybe there's a typo. I'm sorry, I will go through it again. So the idea would be that now I have constructed in such a way that here no element appears where there's an increment where two increments are large away from each other. Because there are some cancellations going on, and that will tell you that when you want to estimate the difference here, what you need to estimate, you can just use the triangle inequality to estimate all these terms here separately. Maybe I just forgot to write down a step, but this was the idea, such that when you now let the p, so the size of the partition go to 0, that this indeed gets small here. And yeah, so the only thing you have to argue now is, okay, I have a psi tilde. So why? But I wanted to have a smooth psi, but this is not so complicated because our psi tilde here was piecewise, so continuous and piecewise smooth. But these kind of functions you can approximate with C infinity functions, and you can show that it's actually enough to have that. But there we also need the details. Okay, so maybe I stop here, but this was the core of the proof. And next time I show you how I use this lemma here to really prove that this fields, so this controlled spaces of controlled path really define a field of Banach spaces. Okay, thank you.
Okay, we have time for a couple of questions or comments.
When you define the signature of a path, it is the path's infinite dimensional coordinate in the tensor algebra space. And you said that when you consider its truncated signature, it has application in data science. Is the n where we truncated it related to the number of samples one has? Could you say a few more words about it?
Well, I think it really depends on the problem. It's of course related to the number of samples. It's of course related to how close you want to have the approximation, and yeah, but it depends then on the problem somehow, of course. So the rule of thumb is the higher you choose, of course, the n, the closer you get to the actual path.
But the 0t, the time, we need to observe the whole process to define it, right? So in application, should you observe so would it be like the whole learning step, or?
Yes. So okay. So what you observe usually are discrete points, of course. So what you observe are discrete points, and so you never observe the path, right? So these are the points, and what you usually do then, you take the piecewise linear approximation, and for this path you calculate the signature. For example, there are these packages, II signature, I think it's called, that actually do that already for you. And so this is what you then, and then you can think, okay, how far do I want to go? I mean, I have to say I'm not an expert. I did not talk about that very much, but it turns out that these are somehow, it's nice to work with the signature up to a certain point. So to use this kind of information, this encoded information, to do certain things with that. But yeah, it's of course also here how many points you observe here will also play a role. And but I think it's hard to say something very general here. So.
Okay, thank you.
But I forgot that actually to give you some references, and maybe if you want to can look that up. So here are many references. So I sent you the notes already, but here are two somehow general references. So this is a primer on the signature methods, already a bit older, and there's a quite recent one from Terry, where they also give somehow a survey on where they use the signature method in machine learning. Okay.
A question?
Does your last result about density of controlled path holds for alpha lower than 1/3?
Yes.
Yes.
Yes. So thank you for that question actually. So we wrote a paper where we did that actually for every regime. So for any rough path, even branched rough path. So this is a concept I did not talk about here, but it holds very general.
So there is more question or comments? No? So thanks again, Sebastian, for the lecture. And see you tomorrow. There is no...
We continue with
Okay. Okay.
after break.
Okay. So there is a break now.
I'm not too sure.